Okay, so welcome back. This is part 4 in our series on understanding electronics, and we're going to cover something that's really important, and you don't see a lot of discussion about it other than kind of general references to specifications. But we're going to talk about thermals. We're going to talk about temperatures, and I think it's really important to get a perspective and a feel for the different types of temperatures that your devices, your components see under normal operation. And what does that mean to the rest of the world? I mean, where is it in comparison to other stuff, and what's really hot and what's too hot to touch and what's incredibly hot, and try to get a perspective on these things so that you have a little bit better understanding about what your components are going through when they are in normal operation. So the first concept is a fairly basic one. I've got here a big resistor. It's a 100-watt resistor with a big metal case, and this is a half-ohm resistor. And the basic concept is as you inject voltage and current through a device, you're injecting more power, more energy, okay? And that energy, like in a resistor, gets converted into heat for the most part, right? In some cases, it gets converted into light. In this case, it mostly gets converted into heat, which means the temperature of this device is going to go up, right? So the more power you put in, the higher temperature you can expect. And of course, that depends on how much external cooling you're putting in. So if you add a fan or you cool it, then it may help to bring it down. But it's basically a balance of how much power is going in, and how much cooling you have depends on the temperature of the device. So this temperature thing, the thermals, is really important. I mean, basically, you're probably familiar with how people deal with these temperatures. Like you've got a big, powerful GPU, graphics processing unit here. You've got these big fans. You've also got software that's used to throttle performance of your device. Like, for example, this GPU might get throttled if the temperature gets too high. There's software in there that will stop the processing or crank up the fan. So there's a lot of stuff that gets done kind of under the hood so that stuff doesn't melt and it doesn't get overheated. That's really important because when it gets overheated, it can get damaged. Now, the other thing is you got to understand what is really bad and what isn't that bad, because I think people tend to think that more heat is bad and stuff is going to melt. And that's not really true. I mean, there is a lot of, like I say, there's a lot of stuff that engineers design in to make sure that it doesn't melt. Just because it's getting hot doesn't mean that's bad, okay? There could be things that maintain it. Usually engineers design your equipment so that it maintains a temperature below the damaging temperature. Okay, so if it's getting really hot and the fans are going really fast, that could be a good thing. That could mean that it's doing what it's supposed to, and you don't have to worry about it. People tend to get very excited and upset, and they don't really understand it, so they think, oh my gosh, this is getting hot and it's going to blow up. Well, maybe not. So we're going to talk about, for example, how to actually measure temperatures using something. If you have a multimeter, it probably came with what's called a thermocouple, which is a temperature measurement device, and it looks just like this. It's got a little bead at the end, and it uses that bead. You put it against the case of whatever you want, of course, making sure you're safe and you don't hurt yourself. You put it against the case and it will measure the temperature. And you can see right here, it's out in free air and it's measuring 23 degrees centigrade, which is about 73 degrees Fahrenheit. But you can use this device to actually measure, in the real world, measure actual temperatures of stuff. You can measure water, ice water, you can measure boiling water, you can measure all kinds of stuff. And we're going to talk about that, and we're going to actually use this to measure the actual temperature of a device as you vary the power through the temperature versus how many watts it's dissipating. Now, there's also, if you have a computer and you're monitoring your computer components, there is software that will track it, measure it, and track it for you, and ultimately you can come out with graphs. This is, for example, for a GPU. It's free software called GPU-Z, plus an additional piece of software that gives you a long-term graph. And this is basically the temperature of your GPU temperature in degrees C over this is a 8-minute period. So I'm starting to run a GPU with a very GPU intensive process. You can see the temperature goes up to, in this case, it flattens out about 86 degrees centigrade, okay? And you can do this. You can either do a real world on a bench test, or if it's on a computer, you can measure it using this software. Okay, so what I've done is I've got a 100-watt resistor here, and it's 0.5 ohms, and I've got my power supply that I am adjusting to put a certain amount of power through this resistor, and I am measuring on my multimeter using the built-in thermocouple. I am measuring the temperature of the case of this resistor as I vary the power. And right now you can see I've got about 5 watts being dissipated by this, and I've got the thermocouple, and what I've done is I've taped it to the top of the case so it doesn't fall off. I'm using what's called Captain tape. It's a very high temperature resistive tape with sticky tape. So you can use it at high temperatures and you don't have to worry about it melting. But anyway, you can see I've got this resistor and it's measuring about 42, a little over 40 degrees centigrade with 5 watts through it. So what I'm going to do is I'm going to make a chart. I'm going to vary the wattage and measure the temperature of this case. And then I'm going to do it with a fan on, basically a big room fan to cool it off, and keep track just so I can see based on how many watts equals how many degrees centigrade for the case. So it should give some good information about how that can vary. Okay, so here are the results of my tests, basically just varying the amount of watts. You can see in the first column, this is how many watts are flowing through the resistor. Again, it's a 100-watt resistor, and I'm just varying the watts. And in these 2 columns with no airflow, it's just with regular room temperature, no forced cooling. And I've got Fahrenheit and I've got degrees. And then what I've done over here is I have added a room fan about 3 feet away and cranked that on to see what the difference is in the temperatures. And you can see I start out with just normal room temperature, no power flowing through the resistor, and I get about 73 degrees Fahrenheit and 23 centigrade, okay? So then, like I showed before, I've got 5 watts flowing through, and I get, with no airflow, I get about 45 degrees centigrade. And when I turn on the fan, I get about 35. So it drops at about 10 degrees with the airflow. And then I crank it up to 20 watts, I get 114 degrees. And then when I turn the fan on, I get only 54. So you can see there's a big difference. It cuts it in half by adding a fan. And then I go up to 40 watts. Again, this is a 100-watt resistor. And you can see I'm up to 180 degrees C with no airflow and 112 with airflow, okay? So if you think about it, there should be a relationship between watts and temperature, right? If you increase the watts, you should increase the temperature, and hopefully that's kind of a linear thing. So you can come up with a number and say, well, you can predict if I multiply the watts times 4, how much should that increase the temperature? So what I've done over here is I've made a graph of thermal resistivity, which is basically degrees C versus watts. And I've got on the bottom, here's the watts flowing through the resistor, and here is the degrees C. And what I've plotted is the blue is with no airflow, and the red is with airflow. Basically, these numbers just plotted here. So you can see that's kind of linear. With no airflow, it's kind of linear. And the slope, if you remember in your geometry class or whatever, if you get the slope here, that tells you what the degrees C per watt. And it comes out to about 4 or 5 degrees C for every watt. So if you increase it by 1 watt, you should increase by 4 or 5 degrees. And that's a pretty linear relationship. Okay, so if I go up by 10 watts, it should go up by 50 degrees C. All right? So basically, you can see that you should be able to get at least a ballpark that say, if I increase the power through my resistor, how much will the temperature increase? Well, you can start by multiplying by 4 or 5 and you'll probably get reasonably close. It depends on the device and everything, but at least you can get a ballpark. And then with airflow, you can see here, you can actually measure and you can see how much it cuts it down with airflow. So this here is a good exercise to go through to get kind of a feel and to get a nice ballpark to say, if I increase the wattage, what can I expect for temperature increase? So with that, now I've got a chart here where I have put down typical temperatures for different things, just so you can get a relative perspective of what different temperatures are relative to each other. So normal ambient, you may know, is like in Fahrenheit about 75 degrees or 24 degrees centigrade, okay? Now, as you go up, the human body is about 98.6 Fahrenheit or maybe 37 centigrade. And if you go a little bit higher, outdoor temperatures, when it's hot out, maybe 110 degrees Fahrenheit or 43 degrees centigrade. So now our 100-watt resistor with 5 watts flowing, we saw that it was about 5 watts, about 45 degrees centigrade, okay? So here is our 100-watt resistor with 5 watts, no airflow, is about 45 degrees centigrade, which is about the same as a hot outdoor summer day, all right? So now what I did is I took my thermocouple, I measured the surface of a CFL light bulb, 23-watt light bulb, and it was about 80 degrees C, okay? So if you touch, which you shouldn't, if you touch a CFL light bulb, it'll be about 80 degrees C. It's about the same as the temperature of hot glue melting, okay? So if you use a hot glue gun, something around 80 degrees C, it will melt, okay? And then you get even hotter, you have a cool oven or a low stove setting is about 200 Fahrenheit or maybe 93 degrees centigrade, okay? Now, the next one is a very important one. You will notice in a lot of electronics components temperatures and a lot of computer temperatures, the point at which things throttle because it gets damaging, is a case temperature of about 100 degrees C or 212 Fahrenheit. And that's also about the boiling point of water, okay? So when you start to see electronic components around 100 degrees C on the outside, you know that on the inside it's a lot hotter, and that's when things start to get damaged. That's why a lot of computer equipment has a throttling point where if it gets, have all the fans on, but it's still getting up around 100 C, you might throttle performance to bring that temperature down. So the next one just above that is our 100-watt resistor when we apply 40 watts. You go back here, your 100-watt resistor, 40 watts, it was about 180 degrees C. Okay, so 100-watt resistor with 40 watts, with airflow is about 112. Okay, so when you get a little bit water, you have, or get a little bit more power, you've got, or a little bit warmer, you get a slow oven, which is about 163 degrees C or 325. And then the thermocouple I talked about, that has a limit. You shouldn't apply more than about 180 degrees C to that because the rubber will start melting. So thermocouples are good, but when you get up around 180, you're getting above its rating. That's 356 Fahrenheit. And that's about the same as our 100-watt resistor at 40 with no airflow, which we just showed. And then an iron, where you iron your clothes, about 188. And then you get a little bit higher, you get a hot oven, which is about 230 or 450 degrees Fahrenheit, as you know, if you cook things in the oven. And then we talked about the Kapton tape, which is the tape that I put the thermocouple on with. When you get around 260 degrees, that's going to start melting. So you've got to be careful when you use Kapton tape to stay below that, about 500 degrees Fahrenheit. And then a soldering iron, the tip of a soldering iron, you're going to set for maybe 320 to 400 degrees Fahrenheit, something in that range. So that's a soldering iron. And then you get way above that. You're talking about the temperature of a candle flame, getting up around 1,000 degrees C or 1,800 Fahrenheit. And then the actual temperature of the filament of a 100-watt light bulb is up in the astronomical range. Okay, so that hopefully gives you a good range of where, what the relative temperatures are. And of course, when you get up around, the temperature of the outdoors, like an asphalt surface in a hot summer, you're getting up around 40 or 50 degrees. It gets really hot, too hot to touch, okay? So up in these ranges, up above around 40 or 50 degrees C, that's getting really hot and you don't want to touch it. So that gives you kind of perspective on, what's boiling water is way above that, and hot glue gets above that. And hopefully this gives you a perspective on what these different relative temperatures are and what the different ranges are. Now, one other thing I want to mention, if you go back to this chart where we applied different amounts of power into this resistor and measure the temperature, notice that when we've got 5 watts, okay, this is a 100-watt resistor with that big old metal case, and we're putting only 5 watts through it, the temperature of the case is 45 degrees C. And we said back here, when you're getting up around 40 or 50 degrees C or over 100 degrees Fahrenheit, that's getting really hot to the touch. So even with only 5 watts through a 100-watt resistor, it's too hot to touch. And when you get up in 10 or 20 watts, it's getting really hot. So again, keep in mind, just because you have this big old 100-watt resistor doesn't mean that it's going to be really cool at 5 watts. No, it's going to be hot. So you have to be very, very careful. You can imagine if I'm 180 degrees C with only 40 watts, less than half power through this 100-watt resistor, this thing is going to be really hot at 100 watts, okay? So, and you can calculate it, 5 degrees C per watt. You can just imagine what it's going to be. So that's why, if you're putting a substantial amount of power, even through a big old metal resistor, you got to be very careful about it, and you don't want it to touch stuff that's going to melt. And you got to go back to this, and you got to get a perspective on, when you're getting up in these ranges, hot glue is going to melt. And, if you have a component, you hot glued it, and it's going to get up in the 100 degrees C, that's going to melt and everything else. So just be very careful and cautious and get a good perspective on what these relative temperatures are. So anyway, I hope that helps. Take care and have a really good day. Thanks.